it works fine. So yes, particle physics in Belgium and particle physics of Belgians at CERN. And where can I start? So I decided to start in 1931 for one particular reason. In 1931, Salvador Dali made an exceptional painting. A painting which came along from his fascination of the emerging thought of the relativity between space and time. He had, as an artist, as well as other people in the society, an enormous interest in science. And he was, of course, as an artist, depicting that kind of interest in the relativity between space and time with these kind of melting clocks. I know there was an interview with Prigogine and Dali, and there Dali was telling Prigogine on these melting clocks, well, basically these are simply camembert cheeses melting in the sun. But I think he was really influenced by the thought of relativity between space and time. What is very important as well, 20 years later, after the revolution of quantum physics, he came along with a very similar painting. And the painting this time looked different. He was breaking down the matter in small pieces, structured, and with a kind of empty space in between, the building blocks of the matter we see around us. And yet again, he was fascinated by physics, by the revolution of physics at that time, quantum physics. Of course, he was fascinated by that because, well, there was the atomic bomb at the end of the Second World War, and you have these missiles here depicting this. But yet you see, artists, society, people in general have a huge fascination for both the largest as well as the smallest parts of the environment around us. And if we say largest and smallest, of course we have to say what is large, what is small. And I try to depict that on this very easy plot. The largest is the universe we see. And I say the universe we see, the visible universe. And that's the size of the visible universe. On the other side, quarks. Quarks are the smallest particles, the smallest building blocks we know of today of the matter around us. Smaller than biological cells, smaller than atoms, we have quarks. And that's the maximum size these quarks have. What we can see with our own eyes is indicated in red. I think with our own eyes we can see probably a few kilometers in the distance. And maybe we can differentiate 1 millimeter from another. But to reach out to the large scales, or to reach out, or to zoom into the small scales, we need technology. And our field is certainly, as you heard previously, enormously driven by an innovation in technology. So these quarks, where are they? These are atoms. That's an illustration of an atom, like you have many of them in the table of Mendeleev. And in the atom, you have the electron, which we consider today as one of the fundamental building blocks of matter. We have the nucleus. In the nucleus, you have these protons and neutrons. I do not know why part of it is skipped. And you have quarks as well, in the protons and the neutrons. And these quarks are what we consider today as well as the most fundamental building blocks of nature. 50 years from now, maybe somebody else is standing here telling you a different story, with more zoom in. But that's what we know today. Nuclear physics is, in general terms, dealing with the atom, the nucleus, and how the protons and the neutrons ending up in the nucleus. Particle physics is more on the other side. It deals with the quarks, how these quarks fit into the proton, and obviously, as you can see now, there's a strong synergy between nuclear physics and particle physics, only already from that picture. How many of scientists, professional scientists we have in Belgium with an interest in high energy physics? We are with almost 300 full-time equivalents. And that is nuclear and particle physics together. If you map them here, you see them scattered over the different experiments and, of course, theory as well. So these almost 300 full-time equivalents are mainly on the experimental side in the CMS experiment in Isolde, and it gives me great pleasure that the next speaker will be the spokesperson of the Isolde facility at CERN. So you have about 1,000 people working in Isolde, and there's a Belgian person which is basically the CEO of that facility over the next many years. We have Na62 as well, and we have other experiments which are not at CERN, like Solitis in Belgium, at the SCK-CON. We have a nuclear reactor, and it's a bit like a sun. Neutrinos are coming out, and we want to study these neutrinos. That's at the SCK-CON here in Belgium. And we have other experiments, I will not elaborate on that, and obviously we have theory as well. In general, 1/3 of our people are working on theoretical elements, 2/3 are working on experimental elements. And we have clearly a gender issue. We are dominated by males. Number of theses. We have about 35 PhD theses defended every year. This is an enormous number. This is 3.2 PhDs defended per year per million inhabitants. This is a fantastic number. Again, the almost 300 full-time equivalents, this time scattered in their position, from permanent to, you may call them postdoc, PhD students, etc. A very good sign is that among the permanent people, 60% of them have an age below 50 years. That's a very healthy cohort of researchers. Maybe less healthy is the amount of engineers we have in our field. 12.5 full-time equivalent, most of them 8 related to IT and computing. Only 2 nuclear engineers helping us, working together with us for nuclear research. 2.5 for particle physics. This is a very small number, certainly for a field which is driven by innovation and technology. The evolution over the years, if you go back 20 years ago and you look to more or less today, the number of scientists has almost doubled. And you see the number of administrative and technical support basically went down with a factor of 2. This is not good. And again, while our research depends on these technology innovations. I just give you a comparison with the numbers I've seen last month at NICEF, the National Institute for Nuclear and Particle Physics in the Netherlands. We have in Belgium, if you sum the postdocs and the PhD students, a number. In the Netherlands, it's about half. While on the side of technicians and engineers in Belgium we have about 25, and in the Netherlands they have almost 3 times more. Altogether, this is a factor of 5 difference from the cohort of scientists and the amount of technicians and engineers that work together with us on these large programs. A factor of 5 difference from the Netherlands. So do not be surprised if we have a major challenge in bringing our technology to society, because these are exactly the people that will help us with that. And we have a technology challenge. We have to make what is invisible, we have to make that visible. And that's a major challenge on the large and the small scales. Just to put this in perspective, we've seen an atom. An atom is very small. You have to put something like 10 million atoms on top of each other to reach 1 millimeter. Atoms are small. And we have to look for quarks in the atom. If an atom would be the size of the Earth, if we look for quarks in an atom, it is the same thing as looking for something smaller than a grain of rice in the volume of the Earth. It is a technology challenge. So we are facing that, and we are very successful in that, and we do that with accelerators. Quantum physics learned us that there is a duality between a particle and a wave. So the particle travels and behaves like a wave. The higher the energy of the particle, the higher the frequency of that wave. So here you go to higher energies. And with these higher energies, you can zoom in a much better way, with a much better resolution in the matter you probe. So the higher the energies, the more powerful you can probe the matter. And that's exactly what we do at the Large Hadron Collider at CERN. So the picture you've seen before, it was designed last century, it was constructed earlier this century, it's operational since about 10 years, and it will be operational for another 20 years. We in Belgium are working on the CMS experiment with today 5 institutions. We are not working on the others. That's also a strategic choice to bring together a sensible number of scientists. And by all means, it is a unique collider worldwide, and it will remain the unique collider worldwide for a while. Hopefully not until my retirement, but certainly for a long time. Very important to know is that the accelerator is financed through the contributions of the different member states of CERN. The accelerator is the laboratory. So it means it's also co-financed using the Belgian contribution to CERN. We heard before from Freddie that CERN is 1 billion euros per year, more or less, and the cost is distributed over the member states according to the GDP of the states in Europe. So the GDP, the fraction of GDP of Belgium in Europe is about 2.7, 2.8%. So this brings us to around 28 million euros per year from Belgium to CERN, and that is foreseen by the federal government. The return, the immediate industry return on investment, so if you have a coefficient related to that and you integrate it over 4 years, then you can basically take a snapshot every year. Over the last 20 years, this is the curve for Belgium. One would be a great return of investment. You see that most of the countries, these are the lines for the other countries, have a return coefficient which is lower than 1. Belgium peaked at the start of this century. Now it's a bit lower, but is ramping up step by step once more. And this was exactly at the time we constructed the LHC, and now we are also going to construct the high luminosity LHC. So there might be opportunities once more. The CMS experiment is about 25 years old. It collects today around 50 countries, 230 institutions, about 3,000 scientists, including almost 1,000 PhD students. More than 1,000 engineers and technicians, and we have about 100 peer-reviewed journal publications per year. It is a collection of a huge amount of people, because also it's a collection of a huge amount of technology. This is the detector, this is the size of a human being. The protons to collide come in here, they come in there, they collide in the center. And this apparatus, this facility, this detector, is going to detect for us and reconstruct the particles which come out of these collisions. It is a great instrument, and it's the responsibility of the partners to construct it, to commission it, to operate it, to maintain it, and of course to do the physics analysis of the data that comes out. And all of this is formulated in memoranda of understanding. This is a very nice picture, a picture I like a lot, taken I think early 2008, when the tracking device was coming in to the CMS detector. And with Belgium we participated strongly in the construction of this tracking device, which was at that moment hanging there at 2 small cables 100 meters under the ground, a bit of a moment of stress. But successful. Belgium and CMS, Belgium is involved since the start. So Belgium became involved 25 years ago. I think Walter was the pioneer, or one of the pioneers in Belgium to make this happen. We have 5 institutions today, 17 faculty members. We are about 4.4% of the authors in that gigantic collaboration. Almost 100 PhD students graduated in our teams on this data, and there are 40 more to come. Very important as well, the inside of this detector, the tracking device which I showed before, has to be upgraded. If 10 years from now we want to collect more collisions at the same time, at the high luminosity LHC, we have to upgrade, we have to design, construct, commission, etc., a new device here. And it's great to know that the funding authorities in Belgium, together with the scientists, have worked together in order to co-finance this upgrade with about 10 million euros. The full upgrade cost of the CMS detector is around 250 million euros. And with that, in Belgium, we are going to build one of the, what is called end caps of the tracking device. So it's sliced in 2.5 meter on 5.5 meter. The other part is going to be built in Germany. This part is going to be built in Belgium. A major technology challenge, major scientific challenge as well, but I think we are ready for this. Some numbers, in my opinion, numbers that illustrate that a small country in such a large collaboration is delivering great science and is recognized for this great science. The operational funding of the CMS detector is proportional to the number of PhD titled authors. So among the 3,000 people, some of them have a PhD, and that's around 2,200 of them, around 1,500 of them. And for Belgium, we are 3.6% of them. So basically, this is the investment of Belgium, the funding agencies and the funding authorities of, let's say, the Flemish and the Walloon governments, to operate, maintain this facility. While we are 4.4% of the authors, while we are 5.3% of the PhD students, we deliver 6.6% of the managers, the coordinators of the different physics teams. In such a collaboration, we have more than 8% of the major conference talks. We have 1 out of 7 chairs of the collaboration board of this whole enterprise. And we have 1/3 of the best PhD thesis awards given worldwide in this collaboration. So again, these are some numbers which I hope convince you that even for a small country, Putting the right people together with the right ambition, you can perform very well in such an enterprise. This date was mentioned already. This is a date which is engraved in the memory of everybody who's working at CERN or ever has worked at CERN. This was the day we discovered the famous Higgs boson, which is coming from the Brown-Glare Higgs mechanism, where we know that Belgium is very proud of. This was a long enterprise. Freddie mentioned it already. These are all the particles we discovered, supporting our theory of particle physics over the last 100 years. And you start with a snapshot, for example here for the Higgs boson. You start with the moment where they were theoretically invented, up until the moment they were experimentally discovered. 50 years between one and the other. And you see, also in the 60s and the 70s, well, the timescales were shorter, but nowadays, if you want to make progress, learning about the fundamentals of matter, it takes time. You have to innovate technology, you have to innovate your thoughts on physics, you have to put together the human and the financial resources, and you have to run these programs. I do not know why this is white. And this is, of course, a picture where we're very proud on in Belgium. Freddie showed you a different picture at CERN. I show you a picture when he was receiving his Nobel Prize medaille. So that's obviously a great achievement for the experimentalists as well as the theoretical physicists in Belgium. This is the picture of particle physics as we know it today. These are all the particles we discovered and are part of what we call the structure of matter. These are the particles we discovered, but which are related to the forces which interact between those particles and the Higgs boson which is there. So in 2012 we discovered the Higgs boson, but this Higgs boson had to connect, to interact with many of these particles. And step by step over the years we are zooming in and learning, discovering these lines. Of course there are many more of these lines to come. This is a picture, a very simplistic picture. These lines, basically every time it's a part of a formula. Well, let me say this is the formula in a very compact form. On a cup of tea, if you like. And that formula tells you how the force carriers interact, how they interact with the fermions, how the fermions interact with the Higgs boson, etc., etc. This blue box here is the thing which came along. That's the legacy, if you like, of the LHC, of the accelerator at CERN. Before that, we had a clear thought since 50 years that yes, this should be the formula to describe the matter in its most fundamental form. But of course, we still had to discover it. We had to observe this part. And since 2012, this thing became a reality and came along. But do not make a mistake. It's not because we can describe with this formula the fundamental structures of matter that we have a profound understanding of what is written there. Just to give you one example. This is how the universe looks like if you look with a different kind of glass. If you look with a glass where you would see what is called dark matter, a kind of matter which is not interacting, as we know today, with the particles we've seen before. It's a kind of a scaffolding of the universe, holding together the whole universe, and by all means, it's 80% of the matter in the universe. And it was not written on my cup of tea. So yes, we know there is new physics, there's other physics out there. We know we have to discover something else. And of course, that means we have to have another kind of cup where you have your own design. We don't know what the design is of that new physics. And that design might be very simple. And yes, typically you start looking for the most simplistic materializations of that kind of new physics. The Large Hadron Collider at CERN is very successful in, for the moment, exploring these simple designs, for the moment excluding these simple designs. It might be something more elegant. Whatever elegant might mean, physicists will recognize this. It might be something more surreal. We don't know. So we have to further explore. But obviously, if we find that new science, that new physics, we have to connect it with the existing cup we have. Making that connection will be, as well, a major challenge. Of course, the first challenge is to find the new physics. In Belgium, we're very proud to put together a consortium of experimentalists and theoretical researchers on the exploration of the scalar sector. The window of the scalar sector, of the Higgs sector, opened up in 2012. So yes, this particle was added. But we have an aspiration to explore how this particle connects to that unknown cup, that new physics. And that can materialize in many different ways. So we put together all the efforts in Belgium exactly to explore this. This is supported by all the funding agencies in Belgium in an Excellence of Science program, BE.H, for the obvious reasons. And we are exploring indeed all the terms on this cup. So again, the interactions between what we call the force carriers with the fermions, the scalar boson with the fermions, the force carriers with the boson, with the scalar boson, and these self-couplings. We have not yet seen all of these couplings in our experiments. For example, these ones we have not yet seen. We still need to explore further. What we have done with the formula we have, we can calculate, we can predict what would happen in these proton collisions at the LHC. And in these proton collisions, many different processes can happen. And here on the x-axis, you see just a variety of the different processes you can think about to see, to detect, to discover in these collisions. And we have done so. We have measured the probability, if you like, the cross-section for these processes to appear. So you calculate them, you measure them, you compare them. And what is clear is that these measurements tend to agree exceptionally well with our predictions. And this over 8 orders of magnitude. Over 8 orders of magnitude, zooming in, this cup does not break. Of course, we are looking as well directly for new physics. For example, this dark matter. If 2 protons, or the quarks in the protons, would interact, they might be able to produce immediately 2 dark matter particles. Well, the properties of these particles are such that you cannot see them in your detector. So it becomes very difficult to discover them, unless these initial protons or quarks would first radiate a particle you know, a particle you can capture in your detector. And with that, we can explore, for example, the creation of dark matter particles in these colliders. But we have not yet found them. And we tend to exclude many of the theoretical models where the mass of these dark matter particles is between 1 and 1,000, maybe 2,000 proton masses. So there is no clear indication where to find new physics, while we know there is new physics. So that means experimental observations will have to guide us. And that means we need more data. But do not despair, there will be more data. As mentioned in the previous talk, from 2010 up to now, up to 2023, we are collecting with the current laboratory, with the current accelerator, the LHC, and beyond that, for another 15 years or so, we will collect more data. Every year here, from 2026, we will collect, the aspiration is to collect at least an equal amount of data as this full period over about 13, 14 years. So yes, more data is coming along. That brings me almost to the end, but I cannot leave this, of course, without saying something how to bring CERN technology, CERN science to society. That is and will always remain very relevant. First, the first thing, obviously, what is our main value? And I would say the people. The people with their talents, with their diversity of talents. The people who work at CERN develop talents they might not be able to develop at other places. For example, on data analysis, computing, instrumentation, how to collaborate across nations, across cultures, management, electronics, communication, name it. There's a huge variety of talents that has to come together in order to make this happen. That is a great value for society. And let me, with a very simple calculation, give you a hint, at least a flavor of where this value can come into. Again, it's a very simple calculation, just looking at numbers, not yet looking at the talents of the people. In Belgium, we have every year a number of PhD students that graduate. About 2,000 of them every year will end up with their talents in the industry, will deploy and use their talents in the industry. Studies have indicated that they typically would have a 17% higher salary compared to what they would have with a master degree. We all know in Belgium we pay quite a lot of taxes on our salary, for good reasons. That means also the tax that goes from the industry back to the government is increased by 17%. If you calculate that over the full career of these people, if you subtract the initial investment, because typically it's the government that is investing the first initial 4 years of a PhD contract, you sum up everything, you end up just from extra tax income, 400 million euros extra tax income per year. Now I put this in the context of CERN. A very recent study indicates that the added value from master to PhD degree is even stronger if you have worked for, let's say, a year at CERN. The number goes from 17 to about 26. If I just say that all of these 2,000 PhD students would have worked at CERN, this number of 400 million would go to 800 million. If this 800 million would immediately come back to science, wow. No? Obviously, this is just about taxes. There's much more than taxes, obviously. There are the talents, there's the know-how, there's the knowledge. The knowledge transfer, as Freddy mentioned. From cryogenics, to vacuums, to materials, to radiation protection, all of these relate to accelerators, detectors, and computing. And all of these relate to elements in society of medical treatment, space applications, safety, environment, etc., etc. About 23 new startups came from CERN Technologies since 2012. Every year, tens of new technologies are disclosed and provided to society, etc., etc. CERN is bringing the technology to society. One of the elements to help bringing the technology to society are what is called the business incubation centers. There are about 10 of these in Europe. You see there's in this case it's a white hole, not a black hole for Belgium. And these business incubation centers, they assist to bring the CERN technologies, the CERN science, the CERN expertise to the market. So they facilitate this. They connect to the scientists, they connect to the industry. And again, you see Belgium is missing there. While I think there is a huge amount of technology also for Belgium to put in society. From the late 60s up to about now, this is the growth in number of accelerators which are operational worldwide. So you reach more than 45,000 accelerators worldwide which are deployed for industrial purposes. Only 200 of them, around 200, are used for fundamental, truly fundamental research. On the scale here, if I would put 200, you would not even see it. Less than 1% of these accelerators are used for fundamental research. And yet, this 1% of accelerators for fundamental research, those are the drivers of the technology for the 99% others. There is an enormous market. And the market value is truly phenomenal, far beyond the level of investment in CERN. An example is particle therapy. You can treat cancers, tumors, with particles, with a particular energy, with a particular dose. And you can deliver that with accelerators. If you go back in the early times of this century, there were only a few centers in Europe that were deploying such a treatment. A few years ago, so 10 years later, let's say, you see many more dots appeared. And if I would make the extrapolation, people made the extrapolation, you see that there's an enormous increase in these centers, only in Europe, elsewhere as well. And obviously, fascinating for Belgium as well, what would happen if an accelerator meets a nuclear reactor? That is called the Mira project in Belgium. The only project in Belgium on the S3 roadmap, where an accelerator will bring in protons on a spallation source, creating the neutrons to create a subcritical nuclear reaction. And with that, you might be able to burn the nuclear waste we have, we are making, and we will make. Putting it all together in one quote, it's a quote of the previous Director General of CERN. In the end, we are working with scientific curiosity that ends up in our pockets. But I would like to add one thing to that. With appropriate investments in both technical and physical talents, it is scientific curiosity which ends up in your pocket. And with that, I thank you for your attention.